Okay, hello, welcome to EE323 Digital Control System mini project presentation. Our topic is inverted pendulum, and the group members is myself, Carlos Babu, and Arroyo Rota. Today we will be presenting our design, which we designed a PID controller for inverted pendulum system. My friend Roya will continue, will start off with our presentation, and thank you, Roya.
Thank you, Carlos. To start off with the content, first we're gonna to introduce the topic, then we're gonna show the system model and transfer function, controller design, result include MATLAB code output, VR simulation, and then we conclude. Next. So a pendulum with a center of mass above its pivot point is known as inverted pendulum. Inverted pendulum is also an unstable system in nature, which is challenging to resolve, and it has drawn attention of many control engineers and other engineering researchers. The inverted pendulum is a fundamental control assignment that frequently used as a foundation for other control algorithms such as PID, neutral network, and policy control. Next. So system model and transfer function. So to design the transfer function of a system, first we have a certain step we follow, as we can see 1 to 4. So the first step, we derive the equation of motion from the free body diagram of inverted pendulum. Then we sum up all the moment around the center of pendulum. So then step 3, we linearize the equation about theta is equal pi, and then we take the Laplace and we arrange the equation. After the step I just mentioned, and we obtain two transfer functions, one for the chart and one for the pendulum. So for our system, we can assume that the friction is 0 because our model was based on a software simulation. So as you can see, we got to our system was minimized to the second order system, and from those two transfer function, we can get the transfer function when we put the parameter of our system. As we can see here, we got the mass of a chart, mass of a pendulum, the length of center of mass, the gravity of acceleration, friction with is 0, and then the pendulum inertia. Then from this value, we get the real transfer function of our system. Next.
Okay, thank you, Roya. I'll be continuing from here, which is controller design, the PID controller. Okay, first of all, since we have two transfer function, we have to design two PID controller. So first, I'm going to go through a pendulum controller calculation. So first, we design the PD controller for pendulum. So as previously mentioned, that after modeling, we come up with the transfer function, and we have a G pendulum, which is GP of S is given by the following equation: 2 over S square minus 43 over 2S. After this, we put it in an open loop transfer function. Then we get the following equation, and applying a root locus design, which is just a mathematical calculations that involving trigonometry, which is finding the angle and using the using the root locus method, which is sum of all the poles minus sum of all the zeros equals to minus 180, then we'll obtain the parameter values. So after performing the calculations, which the calculation was shown in steps. If you can follow, then you can see how the values are obtained. So after performing all the calculations, we come up to our PD controller, which is given as GPD 0.18 S plus 114.07 over S. So, so that is our PD controller. Okay, moving on, we calculate the PI controller. For PI controller, we choose a 0. We place a 0 according to the design specification. So by performing certain numbers, by inputting certain numbers to the system in MATLAB code, we come up to 20.5 as our 0. So we place 20.5, then we get the design specification. So after that, we get the PI controller comes to 0.18 H plus 20.5 over S square minus 43.223. And finally, when you multiply PD and PI, you get the PID. So we get the PID, which is G controller PID in S domain is given as 0.19 S square plus 31.29 S plus 560.5 over S square. And after that, by the help of MATLAB, we convert the Laplace domain, which is a S domain or continuous domain, to digital domain by using C to D function, which the digital controller the digital PID controller comes to 0.016 Z square minus 0.06 Z minus 0.05 over Z square minus 1.73 Z plus 0.77. From here, my friend Roya will continue and discuss the PID calculation for CAT. Thank you, Roya.
Thank you, Carlos. We'll move on to the PID controller design for the chart control. These are the following steps we follow. The same step had been discussed by Carlos. And for example, we already get the two transfer function, one transfer function for the pendulum and one transfer of the chart. So after inputting the parameter, so we get this transfer function of 4.647 over S2 minus 2.9. So from there, we get the S1 of 0.02, okay, 0.0304. This one we get it from the design specification where we saw for the damping ratio and overshoot, and then we get the S1. So moving on, so using the load robust design, we have to find the values of the A and B. So after we obtain the value, so we obtain by calculating first the angle, and we know in the load locus the angle of the order total of the order poles and zero will be equal to negative 180 or plus 180. So placement of A and B. So as you can see, for A, we have A equal to 904 over 10, 0.3 plus 0.2. The 0.2 is where the reference of 0.2. Our reference is 0.2 because we get it from the point of S1. So moving on, so we get our value of A of 200.7102, and then we can find the for the K, we find it by this equation L1 multiply L3 over L1, and we already get the L parameter as shown. So we get the value of K of 0.386. So the overall gain of K for the open loop transfer function, we get it of negative 0.017. Therefore, the PID controller transfer function of the chart closed loop obtained from the Matplotlib as follows. So our PID as shown here is 0.2082 S squared plus 3.69 S plus 5.73 over 0.18 S squared plus 3699 S plus 5.377. And then this PID transfer function, so we convert it using MATLAB, and then we convert it from the S domain to Z domain, and then we get the PID control and the Z domain of 0.893 to Z squared plus 0.284 Z minus 0.128 over S squared minus 1.69 Z plus 0.9605. So from here we get PID controller for a chart. Then I give Carlos to continue with the next slide.
Okay, thank you, Roya. Moving on to Simulink model. As you can see the block diagram given below, we build the system in the united pendulum system in MATLAB Simulink. So why we build this system? Because the transfer functions we want to run our simulation in VR model, but because of our transfer function we obtain, which is the cut transfer function, we don't get the transfer function in negative form, the PID values in negative form. So from there we consult the lecturer, and he told us to tune the controller in using control designer. So from there we build the system in Simulink and tune it according to the design specification. So as you can see from the table below, we have the pendulum and the cut, and the parameters of the PID controller and the system performance, and similarly to cut. So after tuning, we have the PID values, which is given in the column below, and therefore this is the we have the system performance, which we have the overshoot, we have the settling time, which is less than 0.61 second, and the peak value. Similarly to cut, we have the PID values and system performance. So this value of PID, this value of PID controller for cut and pendulum will be used in a VR model, which will be seen in coming slides. So this is how we get our VR parameters for the controller. From here, I give it to my friend Roya, will continue from here discussing the results. Thank you, Roya.
Thank you, Carlos. So moving on for MATLAB result. So first, we see here the pendulum PID controller response in continuous mode, continuous time. So we can see we have a system of overshoot of 20.7 and our peak amplitude of 1.21. Our final value is 1. So we have a settling time of 0.216. So after this, we convert the system to Z domain, and then we can see here in figure 7, we can have the same system response of peak amplitude of 1.2 overshoot of 0.21 at and the settling time of 0.126. So we can see here from after we convert everything from mesh to state, we obtain the same overshoot and settling time. Next. So chart PID controller we follow the same step. We obtain the system response in continuous time. So in the first graph, we can see we have a overshoot of 19.1 and our peak at 1.19 and our setting time of 2.05. So after we obtain the result from the continuous time, then we transfer our system to a PID, and then we have a system response as follow as the same with us in the continuous time. As we can see, we have a overshoot of 19.4 and our peak amplitude for 1.19, and we have a settling time of 2.05. So we can see the system was the same in the S domain and the Z domain. So I give the colors to continue the next slide. Thank you, Carlos.
Okay, thank you, Raya. Moving on to the Simulink model. Okay, as mentioned previously, we build the system in MATLAB, which is the inverted pendulum in MATLAB. Then we build it, we coded it in MATLAB and build the model in Simulink. So after building the model in Simulink, then tune the controller, we get the system performance as shown below, which we have the good response here, which we have the less overshoot, and it settle as less than 20 seconds. So we have so we have the pendulum and the step and cut. So this response will be shown in VRA model, which the values of the PID controller that has been tuned will be shown in will be put inside in a VRA model, and we'll see the simulation that work according to the design specification. So here I will run the simulation in a VRA model, then we'll see whether our PID values work or not. So let me just open the VRA model, close this one. So we have the VRA model here. Okay, let me run the system. Sorry. So we have the position control. We have, this is the controller which we have tuned that has been explained previously. We have these values that has been inserted here. And for the angular, we have the values also here. These values also see that has been shown in the table in the PowerPoint. So let me just run the system and we observe the controller that we designed. So now the system is running. Let's give the disturbance to the, let's move the car. So as you can see, it will settle in less than 20 seconds. So if we can time it, the system will settle according to the design specification. So let me just move it right here, so we can see it properly. Therefore, as you can see, it slowly go down to settle to less than 20 seconds, which shows that the design, the parameters of the PID that has been obtained is work according to the design specification. But one problem here is when you give, because our system is in a fast response system, if we give the disturbance too high disturbance, then the system will go to diverge. So let's see how that will work. So if I give too much disturbance, the system go to diverge. So let's just stop. Sorry. And let me run again. So the system is running, and let's see again. So this shows that the controller we design is work in a VR model. So we'll go back to our PPT, PowerPoint, then we'll continue with the presentation. So as we discussed, the PID values also work in a VR model. So moving on to conclusion, to conclude our project design, we managed to implement the system in the controller in MATLAB, then convert it to digital domain and observe the system response according to the design specification, and also implement the model in Simulink and tune the controller, and finally put the controller value in VR model, then simulate the system, which is shows as our PID values that we have designed was work accordingly. So that's conclude our presentation. Thank you. These are the references that we use. Vinaka.